This is lecture 7. Up until now, we have kind of refreshed our UG concepts, and in the previous lecture or previous couple of lectures, we started to delve into some receiver architectures, and we covered very briefly and in a very high level way. We covered two receiver architectures which are popularly used in the literature. One is a zero IF receiver or a homodyne receiver, another is a heterodyne receiver. And we also saw why would one like to choose with respect to the other. And if you make a choice of, for example, to go with a heterodyne receiver, then you probably will need multiple stages of down conversion, but you do not have the problems of LO leakage or LO feed through. But if you choose to go using a homodyne receiver or a zero IF receiver, then obviously the architecture is much simpler. You have less number of components to worry about, but the problem can be of LO feed through. Now, later on in the course, if we have time, we'll get into how to use homodyne receiver in the presence of LO feed through and still make it work, right? So there are whole lot of digital calibration that goes on in the background to make it work. But having said that, if you are not willing to spend too much time and energy on back-end digital calibration, then heterodyne receivers are kind of the workhorses of most RF front ends. Okay. So now what we will do, we will now switch gears and focus on another intricacy of a RF front end, which is not always evident in traditional analog circuits, right? So let me first lay out the situation, and then after that we will be discussing more about it, right? So what is the situation? The situation is we have an antenna. Then I am not sketching the SAW filter for the time being. It is assumed that there is a SAW filter. So now we have an antenna, and the antenna typically does not sit on the chip. It sits somewhere else on the board, or and after that you have a long routing, and it comes to the chip, right? And you have a chip which has an LNA inside. So this is the chip, and maybe inside the chip you have an LNA. Okay. The moot point that I am trying to make here is that you have a long routing from the antenna to inside the chip. So to give an idea, typically the chip dimensions are of the order of few millimeter, right? Maybe at max few tens of millimeter, but not beyond that. But these cables that connects the antenna to the chip can be few centimeters long, right? Sometimes it can be a feet also, depending upon where you have kept the antenna and wherever is your chip, right? So this routing is of the order of typically tens of centimeter. It hardly ever goes to meter. Okay. So now something weird happens when you take a signal and route it over a long piece of wire. Now a long and short are relative terms, right? So we need to basically characterize what is meant by long and what is meant by short. So in this context, something weird happens if the length of the wire is of the order of the wavelength of the signal that you are sending, right? I will show. Let me just give you what generally tends to happen. Then we'll get into the nitty-gritties of the analysis. So, for example, you take a long wire. A long cable, typical cable that you find in the lab. Okay, and you open circuit it. There's nothing connected on the other end. Okay. And let's say now you connect a voltage source with some resistance I mean, every voltage source comes with a resistance, but let's say you put an explicit resistance there, right? And you observe this voltage. This is a sinusoid, right? So what would you expect? So what is the impedance looking into this line? Nothing is connected to the other end. You would expect it to be infinite, right? Which means that nothing is loaded, which means no current is flowing, which means I should see the same sinusoid at this juncture, right? But as it turns out, it's not the case. You would see this sinusoid at this juncture only at very low frequency. If you plot the frequency plot at this point, right? If you plot the magnitude response with respect to frequency, this is, let's say, omega in, right? And let's say I call this node V out, and I plot V out, right? What would you expect? At DC, at very low frequency, V out should be equal to V in, right? So if I plot V out over V in, your V out should be equal to V in, so you should get some 1, right? But you will see that as you sweep the frequency, this is just an observation, right? If you sweep the frequency, if you go to the lab, do this experiment, connect this V out to a spectrum analyzer, what you're going to see is that it starts dropping, and after a certain frequency, it actually drops to 0. And then after some frequency, it starts going up, and it keeps on doing this. It might not go to exactly 0, but it will go very close to 0. This is what you are going to observe, right? So this is observation. Okay. So this is for the, if you know what I am leading to, right? For all of you who remember undergraduate courses on transmission lines, this should directly ring a bell, right? But in this course, we'll spend slightly more amount of time to refresh this concept and motivate as to why this happens and what are its implications. Okay. So now the question is, why is this happening, and if something like this happens, what are its implications, right? So consider one such implication. It might as well happen that because of this long routing, the signal that is getting transmitted from the antenna, right, does not reach the other end of the cable as is. It might be distorted, or some sort of attenuation has happened. All sorts of things can happen to the signal as it traverses from the antenna to the LNA, right? And all of this is happening because of the long routing, right? So now the question is, why is this happening, and what can we do about it? Okay, so to figure out what is happening, let's delve into slight amount of detail with respect to the transmission line theory, which I am sure you are accustomed to, but it will be helpful for the remainder of this course as well. So let's see. So how can we, essentially the point is, how can we model a long wire, right? So if from our school days, we know that we have read about these experiments, and we might have done these experiments also. If you have a long wire and you send a sinusoidal wave through it, or you send a current pulse through it, and you put some magnet near it, you will see the magnet flicker, right? So which essentially means that there is inductance associated with the wire, right? And because of that inductance associated with the wire, we are getting, there is an effect of a flux, and that rate of change of flux. So the question is, why does it happen, right? And and what can we do about it. So to appreciate why does it happen, um, let me take you back to our school days when we were introduced to electromagnetism for the first time. So you had a long wire and there is a current pulse and you see a magnet move suddenly, right, which is electromagnet, a magnet which is placed close to the wire, or a compass that is placed close to the wire, it slightly moves. So that was one of the ways to understand that moving electric field, moving current creates change of current creates magnetic field, and then we got to know about magnetic flux and so on, right? So which essentially means that a long wire or a wire has some self-inductance, right? So a wire can naturally, if a wire has a self-inductance, and if the return path of the signal is also close to the wire, right? So there will be a return path when a current flows, and if the return path of the signal circuit is also close to the wire, which means there can be some capacitance associated with between that wire and the return path as well, which means I can essentially model a wire as a distributed L and a C, right? So essentially a wire can be modeled like a distributed L and a C. So on, right? I mean, you can have inductance in the return path as well, but I'm not putting it for the to make the figure less cluttered and the associated math slightly simpler. Okay. And note that the convention is to model these L's and the C's as as inductances per unit length and capacitances per unit length. And that's what we are going to do. So this is L. So L is Henry per meter, and this is C. C is also farad per meter. And now if we say that the length of this wire, I mean, we are probably sitting here at x, and this is x plus delta x. So it essentially means that the inductance is L times del x, the capacitance is C times del x. Okay, so we are now trying to figure out what happens, what are the governing equations for the currents and voltages in this long line, right? Now note that when we do conventional circuit analysis, right, using KCL and KVL, we do not assume that there is a del x, right? We assume del x is equal to 0, and we assume that whatever happens at one end of the circuit, the information flows to the other end instantaneously. The inherent assumption is that the speed of the light is infinite, or inherent assumption is that the speed of the light is much more than any other change that is happening in the system, right? So, but if the length of the line is long, that assumption is not valid, right? When I say long, what I essentially mean is that when the length of the line is longer than is of the order of a wavelength, right? Which means that the frequency associated with the wavefront, or rather 1 over time frequency, there is a time period associated with the wavefront, is kind of the order of the time the signal takes to go from one end of the line to the other, which means that inherent assumption is no longer valid, which means we'll have to develop a new model, right? So this is basically that model. Okay, fine. So now let's say the voltage at this end is V of x, and the voltage at the other end of that lumped inductance, infinitesimally small inductance, is V of x plus del x. And let's say again, this current is I of x, and this current is I of x plus del x. All we have to do is establish relationship between I and V in terms of the components available to us, right? So which let's start with V of x plus del x and V of x, which essentially means that V of x minus V of x plus del x, that is the voltage drop across the inductor, should be equal to del t, right, of the current flowing through it, Ix times the inductance, right? The inductance is L times del x, right? Which essentially means that I can write it as this del x comes this side, and under the case of limiting value of del x tends to 0, so this becomes negative dou del x of E of x. So now the stuff that we should be mindful of, which I missed here for the time being, is I have only considered the effect of, I only considered the fact that the voltage waveforms or the current waveforms are functions of space. That is not strictly correct. The strictly accurate thing to recognize is that they are also functions of time. Okay, what we are doing right now is to focus on only one snapshot of time, right? So, but nevertheless, it is definitely better to keep the time here. Otherwise, we might end up making a mistake later on. Okay, so this is minus del v del x comma t is equal to L t, and if I move the plus sign, negative sign that side, I'm going to get this. This is one equation. Similarly, now if I concentrate on KCL, right? If I concentrate on KCL at this node, what am I going to get? I will get I x t x comma t is equal to I x plus delta x comma t plus c times delta x times del v x plus delta x t, or rather dou v dou t, right? So I take this guy on the left hand side, right, and divide by delta x and limit this tends to 0, which essentially means that I get again negative of dou I dou x, or del I del x should be equal to negative c del v x t, right? Okay, so now these two are this is a famous expression where you have two system of, or rather this is a famous system of coupled first order differential equations, and when you uncouple them, that is replace take replace I with v, so you are going to get a second order differential equation, and we all know the solution to this second order differential equation, or rather the solution to this coupled equation, and the solution is as follows. So the solution to this is v of x t is any function f, any function of the form x plus minus some constant v times t, v underscore c, I am giving it the name of v underscore c times t, right? So any function of this form satisfies this system of differential equations. If you do not believe me, you can simply put in the terms and get it verified. So now Now when you see that there are two possible solutions, right? There are two possible solutions that are available for the same function, and it's a system of linear differential equations, which means the generic solution is it can be uh, it can be a superposition of both the solutions, right? So essentially we can say that v of x comma t can be f1 x minus vct plus another function of the form f2 x plus vct, right? Okay, fine. So we need to understand what is meant by these individual terms f1 x minus vct and f2 x plus vct. But before that, maybe we should also take time to figure out what is the corresponding term for I, right? So given that v is known, we can basically plug in those plug in the same value in this equation. You can do it in the next equation also, but let's choose to do the first one, that is del v del x is equal to, so let's take one function at a time. So let's say I take only this function at a time. So let's say I call this v1. Say v1 x comma t is equal to f1 x minus vct. So v del x is nothing but f1 dash x minus vct, right? And note that this is exactly is equal to, this is also is equal to, let me also make it sufficiently clear that I am doing this derivative with respect to x. So this is v x f1 x minus vct. This is exactly equal to, if I take the derivative with respect to time, minus vct, but I also multiply or divide this guy with 1 over vc, right? So I have to divide this guy with vc, right? These two are identical. So this will be helpful in the next step, because I am going to use this, this equation. Okay, so what is this equation telling us? This is basically telling us del v del x that is this, it's basically telling us minus 1 over vc dot t of f1 x minus vct is equal to minus negative of L dou I dou t, right? Negative of L right? So which essentially means that what is I? Well, let me call this I1 because it is associated with V1. So your I1 is nothing but F1 x minus VCT over L times VC. Okay. Okay. So similarly, we can do the same thing for F2. That is, and do the same thing. So this should have been V1. So if I say that V2 x comma t is equal to F2 x plus VCT, then I follow the same steps. So I am going to get I2 x comma t should be equal to, now note the sign. So your this negative term will come as is because it is a part of this equation, but the other negative term is not going to come because it is x plus VCT, right? So which essentially means that your I2 becomes negative of F2 x minus VCT by L times VC, right? So let me then write out the findings. So this is still now it's only brute force maths. There is no intuition. So let me find out. Let me get to the final expressions, and then we'll try to develop the intuition. So your final, essentially, what we came up with, your V of xt on this long where is nothing but f1 x minus VCT plus f2 x plus VCT, and your I of xt is nothing but f1 x minus VCT by L times Vc, negative of f2 x plus VCT by L times Vc, right? Okay. So we end up with these two equations. So we have to make sense of what these f1, f2, x minus VCT, x plus VCT, blah blah blah, and what is VCR, and then we are going to move forward. So the next thing to understand is what is VC. So to do that, we will use the other equation which we haven't used till now. That is, we are going to use this equation, right? So that is dou I dou x equal to negative c dou v dou t. So let me also write it down. Dou I dou x is equal to negative c v dou t. So essentially using this equation. So dou I, and if I to keep matter simple, let me only do this partial on this term, right, and the corresponding term on the top, and I'll basically extend it to the other term, right? So it doesn't really matter whether you're doing it on f1 and f2 because both of them are solutions, right? So I'll just do it on f1. This is without loss of generality. You can do whatever I am going to do, you can do it with f2 also, or you can combine them and do it also. It will not make any difference in the final output, I mean the value of VC. So dou I dou x will essentially be dou f1 dou f1 dou x. So basically this is dou f1 dou x times 1 by L VC, and this is essentially equal to negative c, and dou v dou t, that is nothing but minus VC again f1 dash, right? So now this f1 dash, if you use essentially I have used chain rule. So if I use chain rule, then this f1 dash is same as dou f1 dou x. So this is essentially also f1 prime. Alternatively, if you are not comfortable with this, you can also use this expression. You can also use this expression. You'll get the same results, but essentially I write it down using chain rule. So you essentially get Vc to be is equal to Vc square to be equal to 1 by Lc, or Vc to be is equal to 1 over under root Lc. Okay. So note that L and C are inductances and capacitances per unit length. So this essentially has a unit of 1 over, or rather meter by Henry times Farad, right? So which essentially means that 1 over, under root LC, 1 over under root Henry times Farad is nothing but is nothing but frequency, right? So essentially this has the unit of meter per second. So this is meter per second. So basically it's basically the velocity, right? So what is the key takeaway? The key takeaway is that ultimately your v of x comma t becomes f1 x minus vct, where vct is the velocity with which some wavefront is moving, right? So if I only concentrate on this term, let's forget about this term for the time being, as we have been till now. So what is this term telling us? So this term is essentially telling us this is a function with respect to x and t, that is the location on the line at any point of time. What is the this function will help us get the value of the voltage at any point on the line at any time instant, right? So essentially what we are essentially saying is that if we have a line and I start count my x from here, and let's say this is the x-axis. So let's say at t is equal to 0, x equal to 0, at t equal to 0, x equal to 0, I get v0 comma 0 is equal to f10, right? And let's say at t is equal to 0, x equal to x1, right? So let's say this is x1. What do we get? vx1 comma 0 is equal to f1 x1. Fine. Now what happens at t is equal to, let's say, x1 by vc? What happens at t equal to x1 by vc? At t equal to x1 by vc, vx1 comma t is equal to x1 by vc is equal to f1 of what? So let me pull this one out because this is slightly important. So this will be equal to f1 of x1 minus vc times x1 by vc, which means at t is equal to x1 by vc, vx1 t equal to x1 by vc, or let me just write t equal to t1, t is equal to f1 of 0. So which essentially means that in plain English, the voltage at this point at t equal to x1 by vc, that is x1 away from x equal to 0, is essentially the same as the voltage at x equal to 0, the voltage that was there at x equal to 0 before x1 by vc. right? So it's as if to say that whatever the value of voltage we had at x equal to 0 at t equal to 0 is now present at x equal to x1 and t equal to x1 by vc, right? So this means that in plain English, this implies the voltage waveform, voltage at x equal to 0 has now traveled to x equal to x1 after time t is equal to x1 by vc, right? And has traveled to, I would like to make it more pertinent. I would like to say that traveled to the right after time t equal to x1 by vc, right? And the fact that I have taken any point on the line at x equal to x1, we can generalize it to any point on the line, which means it, what is this equation, what is this implying? This is essentially implying that this represents a waveform which moves along this line as time progresses, right? So essentially this represents a traveling wave, okay? And this negative sign implies that it is moving to the left. And what does a positive sign imply then? So this again is representation of f1 x minus vct. And what is the positive sign implying? X plus vct. It implies that whatever the voltage at x equal to, let's say x equal to x1 has now traveled to the left and is now available at x equal to 0 after time t equal to x1 by vc, right? So why has it traveled to the left? You basically do the same thing. Instead of putting you start off, instead of starting from x equal to 0, you start off from x equal to x1 at time t equal to 0. So you essentially get f2 of x1, and then you assume that you are at x equal to 0 after time t equal to after time t is equal to x1 by vc, right? So it essentially means that your wave has shifted to the left. Okay, the final conclusion is when you have a wave which we have modeled as a transmission line and a wave is launched on it, then you are going to get two waves, one which moves to the right, which is characterized by f1 x minus vct, and another wave front which moves to the left, which is characterized by 2 x plus vct, right? Have I messed up the notation somewhere? No, it's fine. Okay, so typically this f1 x minus vct is referred to as the forward going wave. So this is v superscript plus. This is referred to as a forward going wave, and f2 x plus vct, which is moving to the left, is defined as FV superscript minus, this is backward going wave. Okay. So again, so what is the combined voltage? The combined voltage Vx of t is essentially V plus V minus. And what is the current? Note that current is nothing but F1 over L times Vc minus F2 by L times Vc. The current is nothing but x comma t is nothing but V plus over L times Vc negative of V minus by L times Vc. Now what is L times Vc? This is L times 1 by under root Lc, that is under root L by C, which unsurprisingly has a unit of impedance, and we call this a characteristic impedance. I am sure you have heard of this term before, which is a property of the line because it's basically ratio of the unit inductance and the unit capacitance. So your Ix comma t is nothing but the forward going voltage wave divided by Z naught minus the backward going or the reverse going reflected wave. This is also called a reflected wave. Let me also mention this. This is also called V plus, is also called the incident wave, and V minus is also called the reflected wave. Right? So the moot point is the incident wave and the reflected wave, they combine and add up to form the voltage, but when you are forming a current, there the incident current wave and the incident reflected wave, right, they subtract from each other. The other way of thinking about it is that the reflected current wave is negative of V1 minus V0, and it's a superposition of that. I mean, any one of those interpretations are fine as long as we are consistent, right? So now let's come now that we have certain amount of intuition as to what is happening in a distributed transmission line, right? So it's time to ask the question, why don't we see these effects in smaller dimensions, right? So in order to understand that, let's again go back to that analogy of, let's say I have this voltage wavefront which is F1 x minus VCT, right? The question is, why do we not see the why are distributed effects not visible in within quotes small dimensions? So the question is, why are we not seeing the distributed effects in these small dimensions? So the intuition behind that is, let's assume we have a transmission line which is sending out a wavefront having a certain wavelength, right? So if you have a signal which has a very long wavelength, right? When I say long, which means long with respect to the length of the line, right? So let's say length of the line is whatever is L, and a signal which has a very long wavelength. If it has a long wavelength, then within this L, so if lambda is much greater than L, then what will that wavefront look like within this within the dimensions of the line? So you will hardly see any change in the wavefront, right? So it will almost be like something. So now let's consider the situation that we encountered in the first page, the beginning of this lecture, as to why an observation like the one that is shown here materializes, right? So let's see. at least we'll try to justify the by the effect of nulls. Okay, so now let's assume that we have some transmission line, long transmission line, right? This is R. And let's assume that we have some wave front, a sinusoidal wave front that is launched from this input port. Okay. Further, let's assume that this, it's a monotonic signal that is of frequency omega. Okay, and since this entire system is LTI after steady state, at any point of time, we know that an LTI system must have a frequency omega also. Or the waveform at any point of an LTI system will have the same frequency of that of the input, right? So now let's keep that at the back of our mind as we proceed. Okay. So all we are interested in is to find out. What is the voltage at this node V1. Okay. So how do we proceed? So let's assume that there is at this junction, at any point of time, the forward going wave is V plus, right, and the reflected wave is V minus. Further, let us also assume that the length of this line is L, which means the time the wavefront takes to move from one end of the line to the other is L by Vc, which let's say we call it tau. I should not use capital L because that's what we have been using for inductance per unit length. Let me use small l. Okay, fine. So everything is a complex exponential or a sinusoid, which means that after some time t equal to tau, or regardless whether it's a complex exponential or not, this wavefront, this forward going wavefront after t equal to tau will appear here, right, which means that I am going to get a wavefront here which is V plus e to the power minus j omega tau, where tau omega is the frequency of the input. Okay. Now what about the reflected wave? Note that this reflected wave, the definition of the reflected wave, it is V superscript minus at the input edge, right? So which means this reflected wave essentially is coming from this on the other side of the transmission line, right? So when the reflected wave, when I see the reflected wave here at V minus, which means that the same reflected wave was available at the other end of the transmission line at time tau before the time instant at the input port, right? So which essentially means that I can model the reflected wave as V minus e power j omega tau, right? Okay, fine. Now what about the current waveforms? So I know that the current waveform here is nothing but the voltage waveform by Z naught, right? So I plus and I minus. So I know that I plus is V plus e to the power minus j omega tau by Z naught, and I also know that I minus is V minus e to the power j omega tau by Z naught. Further, I also know that this is an open circuit, right? So the transmission line imposes this time delay and by Z naught and all those all those constraints, but the open circuit imposes the constraint that the total current into an open circuit is 0. So what is the total current? Total current is I plus minus I minus, right? So I know that I plus minus I minus, this is happening at, this is at L, right, at x equal to L. Let's say I call this x equal to 0, this is x equal to L is equal to 0, which essentially means that V plus e to the power minus j omega tau is nothing but V minus e to the power j omega tau, right? Okay. So which essentially means that V minus that appears at the input port, which appears at the input port is a delayed version of V minus that appeared at the open circuited terminal, which means this is nothing but V plus e power minus j omega tau further delayed by tau, right? So which is equal to V plus e to the power minus j 2 omega tau, correct? So now let me mark out the important stuff. So this is important. So this is the reflected wave at x equal to 0, right? So this is reflected wave at x equal to 0, and this is incident wave at x equal to 0. Okay, and now since these are like continuous time waveform, it happens, I mean it is there from t equal to minus infinity to t equal to plus infinity, which means that these two wavefronts are going to, at steady state, they are going to overlap, right? It's not like the wavefront is there for only one instant of time. Okay, if that is the case, what is your total wavefront? Total wavefront or total waveform at V1 is nothing but V plus V minus e to the power minus j 2 omega tau. Alternatively, I can simply write it as is equal to V plus V plus, so this is V plus x equal to 0 at any time t plus this is x at V plus at x equal to 0 at time delayed by 2 tau, right? So that is t plus 2 tau. Okay, so now let's make sense of whatever we were trying to make sense of at the beginning. So assume this is a sinusoid of certain frequency omega, right? And assume that tau is such that the delayed version by 2 tau is equal to half wavelength of the sinusoid, which means that your reflected wave will be exactly the same amplitude but opposite in phase, right? This is if 2 tau is equal to p by 2. What is t? I tau is equal to t by 4. So that is if the length of the line is equal to quarter wavelength, if the length of the transmission line is equal to quarter wavelength of your of the incident signal, then a quarter of the time goes for the signal to go front and another quarter of the time it takes to come back, and when it comes back it meets its own version, because it goes on for infinite time, it meets its own version of incident wave but opposite in phase, so they cancel each other, right? So now you should make sense of whatever we had at the beginning of the lecture, right? So if this is at omega naught, right, if the length of the line is such that 2 pi over omega naught, which is the wavelength, which is equal to one full time period uh, over 2, right? That is half the time period is equal to round trip delay through the line. I should not say if, the way I have drawn it, it's basically saying that the length of the line is such that uh, that half time period is equal to the round trip delay through the line, right? Similarly, if this is the case, it should be now intuitive to understand that it need not be the round trip delay need not necessarily be true for only uh, uh, 1/4. It should not be equal to one only half time period. It can as well be 3/4 of the 3/2 time period, 5/2 time period, and so on, and you are going to see this periodic dips, right? So that is why. Uh, so now note that this is a very uh, weird thing that happens in a distributed system. You are not never going to see this in a system where the dimensions are much smaller uh, uh, than the wavelength of the line that is involved, right? Wavelength of the waveform that is involved. But since in a RF system, the chip has to interface with an external world, which typically is an antenna and a long cable, then we'll have to be aware of what are the potential pitfalls that can happen if we do not take care of this length factor. In the next lecture, we will see that how to deal with these problems, or this how to tackle these potential issues, and how chip designers and RFIC designers ensure that in spite of having these long wires, which are not uh, small with respect to the wavelength of the line, we still ensure reliable transmission of information, right? Okay, we'll stop. Thank you.